Organizers. It's a great conference. It's great to be here. This is the second time I've been at the Newton Institute, and the first time I was a graduate student. And in one of the early talks, somebody announced the thesis, work I had been working on for 4 years. So this is a much more fun conference so far. But okay, so I want to talk about random graphs and applications of Coxeter groups. So there's kind of two different parts of this talk. So what I want to do is the field of random graphs is, I assume, less familiar to most of the audience. So I want to start by kind of introducing some of the background there, say a little bit about that, and then I'll kind of come more to the geometric group theory world, talk about some of the invariants I'm interested in geometric group theory, talk a little bit about writing the Coxeter groups, and then kind of bring these two areas together. So to start, we can ask the question, like, what is a random graph? And so here is, if you search the internet for random graphs, there's various things that show up. So here's the internet in 2005. Actually, sometimes I took the slide out, but there's also, I had a picture of the internet from 1971, which just has 4 nodes. It's a very simple graph. This one's more complicated in 2005. Here's communities of neurons in the brain. That's a pretty interesting graph. And here's Erdos and his collaborators. So no talk about random graphs would be complete without talking about Erdos. And here's a graph of all his collaborators. And this picture is from, I think, 69 or something, or 79. It's interesting. So in all these pictures that I drew, they're kind of things that are constantly evolving. And so one interesting thing about random graphs is that if I wanted to know what do all Erdős' collaborators look like, I could draw this graph. But even when this is drawn in 1979, it's evolved since then. And even though he's been dead for almost 20 years, or more than 20 years now, this graph is still being updated. Like, he had a new paper last year with a collaborator that I think was born after he died. So it's constantly being updated. And so one advantage of sort of randomness is that it gives you a sense for things where sort of the concrete object you might want is sort of changing, but if you kind of have some sense of, if you can do things about generic behavior, you can kind of maybe understand objects that are more concrete as well. So let me get to a more precise definition. So I'm going to talk about Erdos Renyi random graphs. And so there's a bunch of different models of random graphs. So the one I want to talk about is called GNP. People often just call it the Erdos Renyi random model. There's several different equivalent models, or more or less equivalent models. This is the one that is not due to them. It's due to Gilbert, but somehow this is the one that's most popular and most often called the Erdos Renyi random model. So the idea is that this is GNP is a probability space, and it consists of, you fix n and you fix some probability p, and you look at all the graphs with n vertices, where given each pair of vertices, you connect them with probability p. And you do each connection independently, so it's an IID. So this gives you some probability space, but for any fixed n and fixed p, it's some finite probability space. And so what's interesting, and so one sort of special case of that is like Gn1/2 is a familiar space that you would get by fixing some number of vertices, like 10 vertices. G10 1/2 is I fix 10 vertices, and then I have some coin, and I flip the coin, and with probability 1/2, you either put in an edge or you don't, and you go through and you check every pair, and you build some graph. So there's only finitely many graphs with 10 vertices, and so the probability space is some kind of fixed discrete thing. There's some, you can know exactly what the probability of a certain graph occurring or not. What's often interesting to do, though, is to think about what happens as n goes to infinity. So you kind of take the sequence of probability spaces, and so what one then does is you talk about saying a class of graphs being satisfied asymptotically almost surely if you have some. So p, instead of just thinking of p as a fixed function, think of p as being a function that depends on n. So maybe it's a constant function like 1/2, or maybe it's something more interesting like 1 over n or log n over n, or some interesting function. And what you do is for each value of n, you look at the graphs in GNP, and then so you say some property. If you have a property of graphs, that property holds asymptotically almost surely if the probability of being in that class goes to 1 as n goes to infinity. So you sort of take some property, you look at some class of you look at the graphs with that property, and you look at the probability of being in GNP. For any fixed n, you have some probability, and then you sort of look at what the limit is as n goes to infinity. And when that limit goes to 1, then the property holds asymptotically almost surely. So let me give a concrete example. In fact, so let me first, here's 2 concrete examples of random graphs in this sense. Both of them are with n equals 30. The one on the left is p equals 0.3, and the one on the right is p equals 0.2. So you can kind of get a feel for what these graphs might look like. So the sort of properties that one might study, so in the famous paper by Erdos and Renyi from 1959, which really started this what's now an entire field of random graphs, was this sort of beautiful theorem about connectedness. So what they did was they proved that there's some function, which is really log n over n is the relevant function here. And if you look at any probability function that sort of decays slower than log n over n, so any probability function which depends on n, so that p of n is always bigger than 1 plus epsilon log n over n, then if you have that property, then the graph that you get, the random graph you get, is asymptotically almost surely connected. So graphs with this, so anytime you take g and p with this, then the class of graphs that are connected has probability 1. And if you take any function that's slower than that, so you take any function that grows less than, for a fixed epsilon, 1 minus epsilon log n over n, then you get graphs which are asymptotically almost surely disconnected. So you might think a priori that, like, as n goes to infinity, like half the time graphs will be connected, half not. And so what's really striking about this is that there's some sort of sharp threshold, and below that you have the probability none of the time, and above that you have the probability all the time. And this is some just computer, I was curious what the graph looks like if you run this experimentally, so I ran for different numbers of vertices, I think 1,000 graphs at each one of these densities, where the density is like 0.8 times log n over n, or 1 times log n over n, and you can sort of see what this threshold looks like. So down here, anything less than this, almost none of them were connected, and up here, all of them are connected. And you get this kind of fairly fast, sort of smooth transition from being always disconnected to being always connected. And so what I want to do in this talk is sort of explain a way that we can take theorems, we can sort of use this prototype of a threshold theorem and kind of bring that into the world of geometric group theory and talk about sort of in geometric group theory how we have how we might have results like this, where some property sort of never holds and then it sort of always holds. So having said that, let me now turn to geometric group theory and talk about the invariant that I'm interested in for this talk. Okay, so the invariant's called divergence, and roughly it's defined as follows. So I'll be thinking mostly about Cayley graphs, but you can really define this for any one-ended geodesic metric space. And there's different definitions of divergence. I'm giving sort of a rough idea here. There's things that need to be said a little more carefully if you really want to get it right, but this is enough to get a rough idea. So the divergence of a geodesic in a one-ended metric space is you take some bi-infinite geodesic, so that's this kind of line that goes across here, and then what you do is you pick, say, the center of the geodesic, and you look at the ball of radius r. Well, if you just asked how far apart g of r and g of minus r are, the answer is you just sort of follow the geodesic and their distance 2r apart. So their distance between these 2 points is growing just linearly. But what you do is you want to do something slightly more interesting, which is sort of cut out the ball of radius r around the center of that geodesic. So you take this bi-infinite geodesic, you kind of cut out this large ball around the middle of the geodesic, and then you say, well, how far apart are these two sides, these two kind of now half infinite rays that are coming out of that. And so in other words, you kind of take the shortest path, connecting them in the complement of this ball. And it turns out that gives you a function called the divergence function of the geodesic ray. And that function, it turns out, is sort of it gives you an interesting invariant. So what you can do is you can look at, for instance, all the geodesic rays in your space and look at all the bi-infinite geodesics in your space and look at the worst divergence that occurs. And so sort of right. So for whenever you do this, you sort of look at the shortest path connecting them, and then you kind of look at the worst possible geodesic where this sort of path grows the longest, and that gives you some function called the divergence function. And it turns out that the growth rate of that function is a quasi-isometry invariant of the space. So whether that function is growing linear or exponentially or whatever polynomially, those sort of properties, the growth rate of this divergence function is a quasi-isometry invariant of the space. And so for the class of spaces we're talking about, that's a theorem of Drutu and Sapir that this is an invariant. Okay, so let me give some concrete. Well, so first let me say a word about. So there's lots of different applications of divergence. I don't want to talk about really any of them today, but let me just mention a few of them. So understanding that divergence is useful for quasi-symmetric classification theorem type questions. such as Jinying was talking about this morning. It's useful for stability of quasi-geodesics. It turns out if you have a geodesic ray, a bi-infinite geodesic, and you know that it has superlinear divergence, then it turns out that geodesic ray satisfies a version of the Morse lemma. So any quasi-geodesic with endpoints on that quasi-geodesic has to lie sort of uniformly close to it. So quasi-geodesics can't stray far from geodesics that have superlinear divergence. And then there's a number of other applications. So this gives a quantified version of hyperbolicity, some behavior about random walks, etc. Okay, so let me give some examples to start with. So the simplest example is the divergence of Euclidean space. So if you're in Euclidean space, then we know exactly how long a semicircle is, and so that tells us that the divergence of that space is linear. Okay, so it's a quasi-isometry invariant, so that also tells you about the divergence of z to the n. So generalizing that example slightly, you can think about direct products. So it turns out that anytime you have two infinite groups and you take their direct product, then you get a group that also has linear divergence. So this is sort of one of the simplest forms of linear divergence. But it turns out that sometimes you can use that to classify. Sometimes there's interesting classifications of which groups have linear divergence in terms of direct products. So for instance, a right-angled Coxeter group has linear divergence if and only if it's of this form. So the only right-angled Coxeter groups that have linear divergence are direct products. So that a special case of that is due to Donnie Thomas, and more generally, that's a theorem that I proved with Mark Hagen and Alessandro Sisto. And there's versions of that for right-angled Artin groups too. There's other situations where one can prove that all the groups that have linear divergence within a certain class are ones that are direct products. Another class of groups with linear divergence are those that satisfy a law. So this is a theorem of Druch and Sapir. So this includes many interesting classes. So nilpotent groups, solvable groups, those things all have linear divergence. Groups that contain an infinite order element in their center. So for instance, if you take any three-dimensional Seifert fiber space, then pi1 of that will be a group that has linear divergence. So there's sort of another. So these are a bunch of sort of various, a variety of different classes that all have linear divergence. Okay, so on the other end of the spectrum, there's hyperbolic space. Okay, so in a hyperbolic space, we also know what the perimeter of a circle is. It's some constant 2 pi times hyperbolic sinh, and so the divergence is exponential, and we can sort of see this nicely in the Escher picture by drawing this bi-infinite geodesic, which is the one that say goes across the middle of the circle, and looking at these sort of avoidant paths. And I can have a sequence of these paths. Okay, and you see that if you count how far we've gone out along this geodesic, we've only gone maybe one angel and one devil, but sort of the number of things that this divergent path takes is much larger, right? This sort of is growing exponentially as I move out that red path. So divergence in hyperbolic space is exponential, and that's sort of a strong sign of some negative curvature behavior. So exponential divergence occurs in other spaces. It occurs in any delta hyperbolic group has exponential divergence. Any relatively hyperbolic group has exponential divergence, and so this is kind of the example of negative. This is kind of a canonical example of negative negative curvature. Okay, so then there was this long-standing there was a question of Gromov's from the early 90s, which was maybe that's all. So Gromov conjectured actually that in a non-positively curved space, so like for instance the CAD0 space, that curvature is always that the divergence is always either linear or exponential. So it turns out that conjecture was actually proved wrong fairly quickly. So Gersten in '94 proved that there's no such dichotomy. So he constructed three-dimensional CAD0 space, non-positively curved space that has quadratic divergence. So that was the sort of first example that was between linear and exponential. And it turned out that Gersten kind of had just sort of hit the tip of the iceberg with the construction he gave, and sort of very quickly it sort of blew up. That there's in fact lots of really interesting spaces that have quadratic divergence. So there's a beautiful theorem of Gersten's where he had this first paper where he just constructed some weird space, and he says this is a non-positively curved space and it has quadratic divergence. But then he had sort of within the same year he published another paper where he classified exactly which three-dimensional manifolds have what divergence, and he proved that if you have, so there's the geometric cases which which are sort of easy to deal with, and then he sort of dealt with the non-geometric ones, which via Perlman covers everything else, and he proved that that you have linear divergence if and only if you're a Seifert fibered space, and you have quadratic divergence if and only if you're a non-geometric graph manifold, and then otherwise you have exponential divergence. So you either have linear, quadratic, or exponential, and it depends on the presence of hyperbolic pieces or not. If you have a hyperbolic piece, then you're exponential. Otherwise, you're quadratic or linear. Okay, and then since then, so then in the mapping class group, I proved that those have quadratic divergence. Teichmuller space with either the Weil-Petersen metric or the Teichmuller metric. Work of several people shows that those almost always have quadratic divergence. There's a few, like there's a handful of low complexity examples that don't have quadratic divergence, and each one of them is sort of an interesting paper of its own. Like there's a theorem of Brock and Farb that shows in certain cases they're exponential. Some of them are relatively hyperbolic. That's a Brock-Mazur thing. My student showed that one of them has cubic divergence. So anyways, so there's a handful of interesting cases that aren't quadratic, but all except for maybe 10 have quadratic divergence. And then there's the case of Artin groups. So with Charney and I had showed in the right-angled Artin group case that they're either linear or quadratic. In Abrams, Brady, Downey, Deutsch, and Young proved the same thing. And then a theorem of Charney and Paris then sort of generalized that to cover all Artin groups. They're all either at most quadratic. They're all at most quadratic. And so anyways, there's lots of interesting cases here. There's lots of interesting groups with quadratic divergence. In fact, so I wanted to mention, there's so many young people here, I want to mention what is an interesting outstanding conjecture. So I've been sort of promoting this conjecture for almost 15 years now, and it's still unknown. What's the divergence of the outer automorphism group of the free group? So I think it's quadratic. I think there's lots of evidence that it's quadratic. So in fact, some of the evidence is, so with Cornelia Drew, and Lee Mosier, we proved that out FN has at most quadratic divergence. And then Algum Kafir and independently Ursula Hammenstadt, they both proved that the divergence is at least linear. So it's somewhere between linear and quadratic, but exactly where it is and the fact that it's exactly quadratic has remained an open question for quite some time. And so their result is maybe almost 5-6 years old now, maybe even a little older than that. What's interesting about their result is it was proven before people knew hyperbolicity of any of these complexes, so maybe even a few years older than what I just said. And so now that people know hyperbolicity, that seems like it should be enough to prove quadraticness. So that would be a great theorem to see.
Can you have growth strictly between linear and quadratic? I'm thinking of Dane functions.
Yes, so you can. So there's no known finally presented examples that have that behavior, but there's infinitely presented examples due to, for instance, Olshan, Olshansky, and Sapir, where they construct sort of weird examples that have weird divergences. But yeah, certainly in the finally presented world, nothing's known that's even not polynomial or exponential. Let me just make one more remark about this conjecture. So people often kind of, Algum Kafir has two related results about out FN that sometimes get confused here. So she has another result where she proves that for outer space, the divergence is at least quadratic. So outer space, the divergence is at least quadratic, but for out FN, she only gets at least linear. And so there's sort of there's sort of a gap. There's a gap there because she pushes the argument for outer space to get something for out FN, but doesn't get all the way. And so that's been sort of misquoted a couple times.
Is it for outer space but not for the spine of outer space or something? Is that the problem?
That's right. Yeah. Okay. So so let me now turn to right-angled Coxeter groups. So I think probably this audience is maybe generally familiar with them, but let me refresh anyways in case not everyone is. So I'll be talking about right-angled Coxeter groups. So to define a right-angled Coxeter group, we'll fix a graph. Okay. So this is how it's going to tie in with the random graphs. So you fix a graph, and then you define a right-angled Coxeter group by you define a vertex for every for every one of the vertices. We define an order 2 generator, and then for every edge between a pair of vertices, you say they commute. So it's just like a right-angled Artin group, which I think everyone's familiar with, except you add order 2. You make all the generators order 2 instead of infinite order. So it turns out that this gives us a much broader world of things to think about, actually. So a priori, it seems like it's going to be simpler because we've made everything order 2, but we've made all the generators order 2, but it turns out that there's a lot of interesting work going on here. So let me give a couple simple examples. So for instance, if I just had 4 vertices and no edge, then this is just the free product of 4 copies of z mod 2z. On the other hand, the complete graph will just give us direct product of 4 copies of z mod 2z. Up in the top right, I've got a slightly more interesting one. I've got the square. So we saw squares coming up in the earlier talk. So he was talking about right-angled arc groups, and there that was giving me a product of 2 free groups. This is giving me something simpler because, for instance, I've colored sort of the various diagonals. This diagonal here gives me just a pair of z mod 2z's that don't commute. So that gives me an infinite dihedral group. And the red ones, this other diagonal gives me an infinite dihedral group. So I just get something that's virtually z squared as opposed to free cross free. So squares in a right-angled Coxeter group are simpler. They're just virtually z squareds. Okay, so those are kind of the simplest examples. Sort of the next step up of slightly more interesting behavior going on is, for instance, if you take a polygon. If you take any polygon with more than 4 sides, then it turns out you get a group which is virtually a hyperbolic. You get a hyperbolic surface group. So you get something that's sort of virtually a hyperbolic surface. And so you get here hyperbolic groups, right? That's something that doesn't appear in the right-angled arc group setting. In the right-angled arc group setting, they all have z. Except for z, they all have z squareds in them. If it's a connected graph, they all have z squared. So none of them are hyperbolic. Whereas you get lots of hyperbolic things in the right-angled Coxeter group setting. This one here is now a product of a free group with this is like a spine of a book, right? So there's this sort of free group going on the outside, and then there's the spine of it. So it's a direct product of this group, which is a finite group with that thing on the outside. And then I have this group on the right, which is slightly more interesting. It turns out that this is a fundamental group of a fundamental group of a non-geometric graph manifold group. So this is a fundamental group of a 3-dimensional graph manifold group, which is it turns out it's a familiar group that lots of people think about. Virtually, this one is the Crook-Kleiner group, which people know from the Arn group setting, which is sort of the path of length 3. So anyway, so there's some 3 manifold groups that appear here in the right-angled Coxeter group setting. Okay, so these are kind of some of the different phenomena that occur, and we'll kind of turn to understand some of these a bit later. Okay, so what I want to do now is we want to ask the question, sort of what group theoretic properties are encoded in the graph. So one property I didn't say yet is that it turns out that the graph uniquely encodes the group up to isomorphism. So in some sense, everything about the group is encoded in the graph. But what we want to do is then sort of pick out some property that we might be interested in and see to what extent that's encoded in the graph. So the simplest case of this is, when is the group finite? Well, the right-angled Coxeter group being finite can completely be read off in terms of the graph. The group is finite if and only if the graph is a clique. So if you have if the graph is a complete graph, then you're finite, and those are the only finite right-angled Coxeter groups that occur. Those are the only the finite right-angled Coxeter groups. So that's sort of an easy case. Something that becomes non-trivial is that it turns out, this is the theorem of Mike-Mahalik, that a right-angled Coxeter group splits over a finite group if and only if there's a separating clique. So now, obviously, if you have a separating clique, right, there's a complete graph in there. That's a finite graph. It split the group. So to see that the existence of a separating clique obviously implies splitting over a finite group, but the other direction is non-trivial. In particular, it means that if you have a right-angled Coxeter group but it splits over a finite group, in fact, it splits as kind of, he calls this a visual decomposition. You can sort of see it in the presentation graph that there's two sub right-angled Coxeter groups, and this the big right-angled Coxeter group splits over the smaller one over a third smaller one. Okay, so that's the theorem of Mike-Mahalik's. Turns out that it's a direct product if and only if the graph is a join. So I wanted to sort of put that up just to kind of put up the word join too. So what does that mean? So a graph is a join of 2 smaller subgraphs. If a graph is a join, if there's 2 subgraphs, subgraph A and subgraph B, and every vertex in subgraph A is connected to every vertex in subgraph B. So that gives me a direct product of the 2 of them. But conversely, anytime a right-angled Coxeter group is a direct product, it comes in this very simple way. It comes out of direct products of sub right-angled Coxeter groups. And lastly, this is a theorem of Mousong's. A right-angled Coxeter group is hyperbolic if and only if there's no square in the presentation graph. So again, a square in the presentation graph gives you a z squared in there, so that's obviously an obstruction to hyperbolicity. That's the only obstruction to hyperbolicity, is what Mousong proves. Okay, and one can go on. So there's some other ones. I'll come back and talk about some additional properties. In fact, I'll spend much of the talk talking about some other properties, but let me turn to ask, how common is hyperbolicity? right? So Mousselong's theorem tells us exactly when it occurs. So the group is hyperbolic if and only if there's no squares in the presentation graph. So from the kind of Erdos-Renyi point of view, how often does that occur? How common among, so right, we know how to build random graphs using the Erdos-Renyi model, so that gives us a way to build right-angled Coxeter groups. So how common among right-angled Coxeter groups are those that are hyperbolic? Well, so it boils down by Mousselong to understanding which graphs don't contain squares. Okay, well, so if you have a graph with n vertices, then there's n choose 4 sets of 4 vertices inside those, right? If you're going to have a square, it's going to have to be built out of 4 different vertices. And then what does it mean to have a square? It means that you have, right, there's with probability p to the 4th, you have these 4 edges in. And with probability 1 minus p squared, right, 1 minus p is the probability of not having an edge, so you have to not have these 2 diagonals. So the probability of having a square is p to the 4th times 1 minus p squared. So what's often, so the case in terms of random graphs, the case where p is going to 1, in that case we're sort of approaching having a complete graph. And in the right-angled Coxeter group case, that's sort of a degenerate thing because we're just getting a finite group. So what we're going to be interested in is cases where p is bounded away from 1. So maybe p is constant, or maybe p goes to 0. But in either way, we want it to be bounded away from 1, in which case if we want to figure out the expected number of squares, it's just going to be the product of n choose 4 times this probability, and if that probability is bounded away from 1, it's just of the order n to the 4th times p to the 4th. Okay, so the expected number of squares is roughly n to the 4th times p to the 4th, and then you can just use the second moment method, and Charney and Farber did this, and they proved that if you have a random right-angled Coxeter group, it's hyperbolic if and only, I wrote if, but it's really if and only if, so it's hyperbolic asymptotically almost surely when n times p goes to 0. Okay, so in other words, if you take p that's less than 1 over n, then you get a group which is hyperbolic, and if p is bigger than 1 over n, you get something that's not hyperbolic. That's what Charney and Farber proved. So in other words, it's extremely rare. So it's only in these cases where you have p that's very small, p less than 1 over n, that's not even the connectivity threshold. That's the threshold for being hyperbolic. And so, whenever you have p bigger than, p is bigger than 1 over n, then you're not going to get something that's hyperbolic. So despite sort of Gromov telling us that sort of the random group should be hyperbolic, and despite the fact that we know that sort of generically hyperbolic three manifolds are hyperbolic, turns out that if we look at right-angled Coxeter groups, most of them are not hyperbolic. So we've got to turn to some other sort of behavior in order to understand them. So with Mark Hagen and Alessandro Sisto, we proved a theorem that tells us about what some of the behavior is. So we proved, so this is not a random theorem, this is back to sort of a concrete theorem about any fixed graph. If you have any fixed graph, so any one-ended right-angled Coxeter group, either it has at most polynomial divergence, or else it's hyperbolic relative to a canonical and possibly empty collection of subgroups, each with polynomial divergence. So either you have polynomial divergence, or you're hyperbolic relative to things that have polynomial divergence, and which can be sort of read off from the graph. And in this later case, as I mentioned before, relative hyperbolicity gives you exponential divergence. So either you have at most polynomial divergence, or you have exponential. So we kind of rule out in this realm this kind of intermediate growth. I should mention that this is a version of this was mentioned yesterday. Genevois has a generalization of our theorem where he proves this for sort of more generally for graphs of groups. Graph products. Yeah, graph products. I said that, right. So for graph products, so Coxeter group is a right-angled Coxeter group is a simple case of a graph product. So for more general graph products, he proves the same sort of dichotomy that you either have. He framed it a different way, but either you have relative hyperbolicity or you get relative hyperbolicity versus, with respect to things which are, which his result will give the same sort of criterion that you get these things with polynomial divergence. Okay, so that was the theorem that we started with, but we actually proved a sort of slightly sharper version, which is that this exponential / polynomial this dichotomy can be determined in polynomial time from the combinatorics of the presentation graph. So if you look at the presentation graph, you can just run this polynomial time algorithm and read off exactly whether or not it's relatively hyperbolic. And if it is relatively hyperbolic, it's going to be relatively hyperbolic relative to some right-angled Coxeter subgraphs. So there'll be some sort of finite collection of disjoint subgraphs, and you'll be able to read off exactly what it's hyperbolic with respect to. Otherwise, it's going to be polynomial divergence. Otherwise, it's going to have polynomial divergence, and then we kind of get some sort of balance given any particular graph what the polynomial divergence is. Okay, so then this left us with the question of what does the random right-angle Coxeter group look like? So we've already kind of ruled out, we know exactly when it's hyperbolic, and now there's sort of a trichotomy, right? Either it's hyperbolic or it's relative parabolic with respect to non-trivial sort of subgroups, which I'm sort of implicitly containing in here. So when I say relative parabolic, I allow for the empty collection of subgroups. That's the hyperbolic case. But so it's either hyperbolic or it's non-trivially relative parabolic, or it's going to have polynomial divergence as this trichotomy, and we've already ruled out hyperbolicity. So we can then ask sort of what's going to happen, what happens generally.
Sorry, Jason, are the subgroups Coxeter subgroups?
Yeah, you can see them in the graph. So just like the same way with this thing with splittings, we can read them off from the graph. And yeah, they're Coxeter groups. Okay, so let me just say a theorem that pairs with this well. In fact, the theorem that motivated us to prove our theorem is a theorem of Pahlavi-Dani and Ann Thomas, where they proved that every order of polynomial divergence occurs in some one-ended right-angled Coxeter group. So right, I had mentioned before this sort of old conjecture of Gromov's about whether there were things between linear and exponential. So it turns out there were things of quadratic divergence, and then it took quite a long time to figure out whether there were anything. So then there was kind of a follow-up question of what happened between quadratic and exponential, and it took a very long time to find anything. And so Cornelia Drutu and I produced some examples that had cubic divergence, and then in fact we found things that had polynomial divergence of any degree, and Natasha Bakura independently found things that had any polynomial degree. But both of us, in both those constructions, we had to sort of construct something. Whereas what this Dani-Thomas theorem now says is that in fact there's these naturally occurring things that have polynomial divergence. So there's right-angled Coxeter groups that have polynomial divergence, and you can find one for any given degree. Okay, so let's now turn to the question of how common. So we now know, unlike in right-angled Artin groups where it was either linear or exponential, here there's some things that are it was either linear or quadratic. Here there's some things that are even exponential, and we have every degree of polynomial growth, polynomial divergence. So the theorem that I proved with Falgas-Ravry and Mark Hagen and Alessandro Sisto is the following. So we proved a threshold theorem for right-angled Coxeter groups. And so our threshold theorem says the following. It says that if you have some probability function which is bigger than n to the minus 1/2 power, then the right-angled Coxeter group you get has quadratic divergence. So anytime, and again, I need that p is bounded away from 1, because otherwise everything degenerates. But as long as p is bounded away from 1, and if then you get and you're bigger than n to the minus 1/2, then you get quadratic divergence. And on the other hand, if p to the n is small, if it's less than n to the minus 1/2, if it's less than that threshold, then the right-angled Coxeter group has at least cubic divergence. So you get this kind of hard split. You either have at least quadratic, you have exactly quadratic if you're in one range, and otherwise you go to at least cubic. And I've got, let me put up sort of a picture of what this looks like. So here's actually, so unlike the other graph, which only took about an hour to run, this is like 10,000 hours of computer time to compute this. But this is a graph of this is what it looks like to actually kind of take random graphs at various numbers of vertices and at various densities and see how see what their divergence is. And this is what the threshold looks like to go from having cubic divergence or more to having exactly quadratic divergence. There's this extremely sharp threshold. This is sort of even, you can see this is much steeper than what happened in the case of continuity.
If I remember rightly, and this is still below the connectivity threshold, is that right? Or
no, this is above the connectivity threshold. Yeah, yeah. So the connectivity threshold is log n over n, and now we're at n to the minus 1/2. They're negative it's always confusing because they're negative exponents. It took me a long time to feel comfortable working with them, but yeah, that's right. So yeah, right. If you're below the connectivity threshold, you're going to get something that's going to be it's going to have a free splitting, and so you're going to have exponential divergence. Okay, so what I want to do in the remainder of this talk is give some of the ideas that sort of go into how we prove this. And there's sort of a mix of combinatorics, which I'm not going to really talk about, and then sort of there's some geometry also. But I want to give a little bit of a flavor of what happens. So what's key in characterizing quadratic divergence is sort of building the right structure. And actually, the idea for this sort of square graph structure comes out of it's sort of a lot of this is in a theorem comes out of some work of Pahlavi-Dani and Ann Thomas. So there's an object that we call the square graph. So given a graph, the square graph associated to that graph has vertices, one for each induced force cycle, so each square, and they need to be induced squares. So those are the vertices. And then you put an edge anytime two squares kind of overlap. Their intersection contains one of the diagonals. It contains the diagonal of the squares. So I'm going to show a picture of what this looks like. So here's this, like, at least my favorite right angle Coxeter group. Right, this is this sort of three-manifold group, that I showed in an earlier picture. And so there's lots of squares in here. So you can see lots of induced squares. And here I highlight one in red. So there's an induced square. So in the square graph, I would put down one vertex for that. But then there's another induced square. For instance, there's this blue one. Okay, that blue one gives you another square to put another vertex in the square graph. And now the red one that I showed before and the blue one, they overlap, and they overlap in this purple graph down here. Now that purple graph down there contains this diagonal in particular, which was the diagonal of both the red and the blue. So you would connect those by an edge. So as you start to draw the square graph, I've now told you how to draw two vertices in one of the edges, and then you kind of go around and you complete this picture. You kind of look at every possible square, you write them all down, and you get some graph. Okay, and that graph can be quite complicated. But a graph is, we say a graph is CFS, constructed from squares, if there's some component in that square graph which contains all the vertices in the entire graph. So the entire square graph need not be connected, but there's some connected component in the square graph which contains, which sort of has, which you can kind of travel through and reach all the squares. So one way to think about this is you can think about some kind of evolution process where you find some square, and then you can flip from that square to another square by moving by finding a new one that shares that diagonal. And so being CFS means that there's some starting square you can start from, and you can kind of propagate this process out and reach every vertex in the graph. Okay, so that's the CFS property. And so a theorem of Ivan Levkovitz from this year. So he's a PhD student of mine who's graduating. This is one of the key results in his thesis. So he proves that a right angle Coxeter group has quadratic divergence if and only if its presentation graph is CFS and it's not adjoined. So you want to rule out joins because you want to rule out the things that have linear divergence. So CFS includes all the things that are direct products, right? Includes all these joins. So it has quadratic divergence if and only if its presentation graph is CFS and it's not a join. So this gives a complete characterization of those with quadratic divergence. And moreover, he proves that if you don't have this property, then you're at least cubic. So this generalizes. So Ann Thomas and Paul Vidani had proven something similar if you had a triangle-free graph. So they proved that among triangle-free graphs, you get a classification like this. But among random graphs, they all have, like random graphs generically have lots of triangles in them. So if you wanted to have a statement about random graphs, this theorem doesn't help you at all, whereas this theorem now gets you all the way. So this is a complete characterization of graphs that have quadratic divergence. Okay, and so how do we do this in practice then? How do we find quadratic divergence? It's funny, it doesn't show up very well on the screen. It looks fine over here. But the laptop's too small to hold up. Okay, so how do we use this in practice? So we want to know how we get from this property to finding quadratic divergence. Well, let me sort of show how this theorem sort of works, right? So if we have a graph, then we can call, if we have an induced subgraph, we call it a suspension if it consists of sort of a pair of vertices that are connected by an edge, but those vertices are all connected to some kind of common subgraph in the middle. So in this picture, I've drawn kind of these two green vertices here, and they're all connected. Each one of those is completely connected to every one of the red graphs, and so all the edges emanating from the top green one I've done in purple, and all the ones from the bottom one are in yellow. So this is this sort of graph that sits in, this is some graph that sits inside my ambient graph, and that's the suspension. And so the nice thing about a suspension, right, is that this is a join of two graphs. It's a join of the two green, it's this pair of vertices, which was like the core of the suspension, and everything else, it's a join of those two graphs, so that's a direct product, so that has linear divergence. And it turns out, and these are quasi-symmetrically embedded, it turns out. So those graphs have linear divergence. So the subgraph associated with that has linear divergence. On the other hand, right, the connectivity of the square graph means that Right. The connectivity of the square graph means that we can find some. Right. The simplest case of a suspension is just a square, but maybe we had even something bigger like we had. But you have some square that you can start with, and then you can now propagate that among these non-edges to fill out more and more of the space. So I've now had this suspension, which I've now drawn completely in red, and now since this graph here is CFS, I can now have these two other green vertices, and I can kind of find a square that connects to them. So what that amounts to, if you think inside so this is inside the presentation graph. In the Cayley graph, along the original square, we had some direct product, and now we have this new green square that we've brought onto that, and they overlap along this non-edge. And so this overlapping along this non-edge means that we have an infinite cyclic group. So we have this original big direct product, and now we have this new green direct product, and the way they kind of relate to each other is they have some infinite diameter overlap. Okay, and so then the fact that this thing is CFS means that I can now promote this to kind of fill out the entire graph. So I can fill out the entire graph by sort of chaining together these squares. And now I've chained together a bunch of things that all have linear divergence, and so this whole space now has at most sort of, it turns out like you can find these linear chains of linear divergence, so the whole space will have at most quadratic divergence. And then there's quite a bit of work, so the key work in Leibniz theorem is proving that this thing has at least quadratic divergence anytime you have this condition. And so I don't want to talk about that now, but so then once you have this characterization of what the divergence is in terms of CFS, then the next step is to apply some probabilistic arguments and sort of do some probabilistic combinatorics to make sure that you can find sort of an appropriate suspension, and make sure you can find that you can find a large enough suspension, and then you can find other things to chain onto that, so that you can prove that sort of the random graph has this process, or has this structure on it. Okay, so that's sort of the rough idea of what we do. And I want to just sort of say, so there's a bunch of different things that this sort of, this leaves open, which is what happens, what other sorts of behavior can occur. So we kind of get this sort of fine structure of exactly when things are quadratic and when they're not, when they're at least cubic, but the rest of the world sort of remains open. And so sort of we know at very low thresholds you get hyperbolicity. We know at some threshold above that, at some kind of medium range threshold above that, everything is quadratic. The world in between has remained sort of mostly open. So we have some theorems in our paper, like we showed that at n to the minus 3/4 with Mark Hagen and Erdos and Sisto, we proved that below n to the minus 3/4 you get things that are generically relatively hyperbolic. So there's sort of a range that you get relative hyperbolicity, but a sharp threshold for relative hyperbolicity is not known. Sharp thresholds for other divergences are not known. So sort of there's a whole world here that's sort of open that I think has lots of questions that I hope people are interested in thinking about. And let me just sort of end with a picture here of, I see this didn't reproduce very well on the screen either, but what this picture is this is a picture of a graph that comes from real data. And the real data here was MEG imaging of a brain. So this is sort of from some sort of electromagnetic imaging of a brain, and we got these graphs. And so Mark Hagen and I have been working with biologists to sort of understand. It turns out that it looks like using the sort of some of these graph theoretic techniques we have, you may be able to recognize some structures in the brain in ways of kind of recognizing maybe some functional behavior from brain data involving properties that sort of come from geometric group theory. So maybe having said that, I'll stop there.
Are there any questions? Yes.
Sorry, when you speak about computer time, what exactly do you mean?
Yeah, that's a good question. So I ran them on a cluster, and so I had a cluster of like 1,000 computers, and then ran them for a bunch of time, and I sort of computed what the sum total of all the time was it took. It didn't actually take an entire year, but it took a weekend on sort of a massive supercomputer. Which it turned out, so right, the way I had, actually the way we, I should say, the way we discovered this theorem is kind of interesting. So we had, right, in this, when Hagen and Sisto and I had proven this theorem about either having relative hyperbolicity or having polynomial divergence, we didn't know which sort of behavior to expect. And we proved a theorem which was a theorem we were excited about at the time, although it turns out to be sort of, you know, a much weaker theorem than what's actually true. We proved that for gn1/2, then asymptotically almost surely it had polynomial divergence. So that was the best we could prove at the time. And so we sort of ruled out exponential behavior, but we didn't know what happened. And a priori, the order of the polynomial could have gone to infinity as n went to infinity. And so what we did was, so I didn't know how to code at the time, so I ran a summer RU, and I had I got some students that were kind of good coders, and I had them write a program to sort of compute what sort of divergences occurred for gn1/2. That was what I wanted to know. And they ran this code, and it took a while to kind of get it working and running, and then we ran it, and sort of, the numbers it spit out kept saying like quadratic divergence, like 1 of cubic divergence, quadratic divergence, like it was like, I mean, I was convinced that sort of how these undergraduates didn't know how to code, and so I then had to learn how to code myself. But it turns out that you knew that there had to be a theorem there. If that was actually right, that sort of you were getting quadratic divergence every time, there had to be a theorem that proved that, and then sort of that inspired us to sort of really set our goals on a much stronger result and improve quadratic divergence. And so then once we wanted to do that, we started constructing, like we started getting a bunch of different behavior. We wanted to see what happened not just at gn1/2. But we thought that, we weren't sure whether that quadratic was an artifact of it being a constant probability, and so we ran a bunch of computer simulations.
Is that the brain of a geometric group theorist?
Yeah, it might be. I don't know. But they probably wouldn't advertise. So this is actually interesting data. It was connected, I think, from Imperial College London. This is data where, so they do MEG imaging, and they do it in a normal state and then in an altered state. And the altered state in the case of this study was they gave all the patients LSD. And so what's kind of cool though is that we have all this data of like, control state and on LSD, and using kind of CFS and using some related properties, like I can tell whether someone's on LSD or not by looking at a MEG image of the brain. So, I mean, it's probably an expensive drug test, but it's.
You said sort of that your theorem is about quadratic divergence.
Right.
So would you also expect a threshold when you take cubic convergence or divergence or polynomial degree n?
Yeah, it's a really good question. So I have two different hopes about this, and they're sort of mutually orthogonal. So they're actually just contradictory. So like one hope is that like maybe for every order of polynomial you get some threshold, and they kind of maybe accumulate on something as you reach the relative hyperbolicity threshold. That's one hope. Another hope is that maybe that doesn't happen. So what's interesting in random graphs is there's something called, so something interesting happens at the threshold 1 over n. So at 1 over n, you get what's called so 1 over n, it turns out, is the threshold for having a giant component. So if you get a random graph, then you can ask like how big the largest component is in the graph, in the case it's not connected. And it turns out that the size of that graph grows, it's like log of n, and then it starts to get bigger, and then right at 1 over n, it goes to n to the minus 2/3, and then all of a sudden it jumps, n to the 2/3, and then it jumps to being linear. So you get what's called a double jump, sort of at that one threshold, all of a sudden everything happens. And so another thing one might think would happen is maybe there's some threshold for what these, maybe there's kind of some threshold where all of a sudden you jump from being some fixed polynomial order to being relatively hyperbolic, and like everything happens interesting like right at that one fine point. And so I don't know which, those are like two possible pictures that could be. I don't know which one it is, but I'm interested in finding out. I mean, what's remained one of the difficulties for now is we give a very in our paper we give a criterion for being polynomial divergence, but what we do is we get an upper bound on what the polynomial is. And so, in the case of quadratic, there's a kind of a very clean characterization of exactly which ones have quadratic. We have a very clean characterization of which ones have polynomial divergence, but understanding which ones are polynomial divergence of order n is more delicate. And so someone needs to kind of work out that precise combinatorial framework in order to make the next steps, I think.
And when you were doing these, or when your students were doing these computations,
Yeah.
what input were they using for the graph? Because you might want to use different forms of storing the graph depending on how
Right,
fast it is, how.
That's right. So I've got actually a whole arsenal of code now that does this sort of stuff that I've written. But I can take any graph that you want. I was building random graphs in GNP, but I've also built random graphs and like there's other models for random graphs. There's the Strogatz-Watts model. Like I've built some things in those models, and it's interesting to know as you sort of vary which model random graphs you take, sort of what sort of behavior. But yeah, we were doing things in GNP at different densities.
More questions? And let's thank Jason again.